Welcome back to Neural Intel. We're going to dive deep today into a new resource. It's called UniOcc, and it's all about occupancy forecasting and prediction in autonomous driving. I think you'll find this pretty interesting.
Yeah, it's a really cool development, especially if you're into the tech side of AI and ML, all those advancements, and especially how it all ties into self-driving cars and how they make sense of the world. UniOcc really gives us a new way to look at this whole area.
That's a great way to put it. We've got the paper right here, all the technical details, and we really want to break it down for you today. What exactly is this benchmark? Why is it technically such a big deal for the field? And what does it tell us about where we're at right now with perception in autonomous driving?
We're going to focus on the technical stuff, the nitty-gritty, like always.
Exactly. No ethical debates or anything like that today, just pure technical analysis. So let's kick things off by talking about how these self-driving cars actually see the world around them. And the key concept here is occupancy grid maps, OGMs.
Right, OGMs. It's like a digital map. Think of it like a blueprint, but for the space around the car. So it divides the environment into all these tiny little cells, like a grid. And each cell tells you if something's there, if it's occupied, or if it's empty, free space.
So it's basically a real-time snapshot of what's around the car.
Yeah, exactly. And it can be 2D, like a bird's eye view, or 3D for a more complete picture.
And once you have this occupancy grid, there are two really important things that the autonomous systems need to do. First, there's occupancy prediction.
Right, occupancy prediction. So you're taking all that raw data from the sensors, cameras, lidar, everything, and using it to figure out what the occupancy grid looks like right now in real time.
Like taking a quick picture, but with a grid instead of an image.
Exactly. And then the second thing, even more critical for safety, is occupancy forecasting.
Okay, so this is where it gets really interesting, right?
Yeah. Because with forecasting, you're taking that current understanding of the occupancy grid and trying to predict how it'll change in the future. Where are things going to move? How will the scene look in the next few seconds?
That's crucial for making sure the car can react to everything happening around it.
Absolutely. It has to anticipate the movements of other cars, people walking, everything, so it can make safe decisions. Now, there's been a lot of progress in both these areas, but the people behind UniOcc, they saw some big limitations with how things have been done so far.
So they saw some technical issues holding back the field.
Right. And these limitations are pretty fundamental. They impact how we train these systems, how we evaluate them, and even how they represent their environment. Like, for example, one big problem is the quality of the data we use, specifically the occupancy labels and the metrics we use to judge how well the systems are doing.
So the data itself might not be perfect.
Exactly. A lot of the data sets we use, like nuScenes or Waymo, they don't actually have official high-quality labels for occupancy. So what have researchers been doing? They've been using what we call pseudo-labels.
Pseudo-labels? What are those?
It's basically like they're estimating the occupancy labels, usually from other data like LiDAR point clouds.
Yeah.
So they use where the laser beams hit and bounce back to try and figure out the shape and position of objects.
It's like trying to draw a picture by connecting the dots but only having half the dot.
Yeah, something like that.
Yeah.
And that can be a problem, right? Because these pseudo-labels might only capture parts of objects that reflect the laser light. So you might not get the full, accurate 3D shape.
Like you might get the outline of a car, but not the whole thing.
Exactly. There's a figure in the paper, figure 4, that shows this really well. A car shape from OCC 3D, which is a common technique for generating these pseudo-labels, and it's really incomplete. It's missing big chunks.
Okay, so if the labels we're using aren't accurate or complete, how do we even know if our models are doing a good job? How do we trust the metrics we're using?
That's the big question, right? And it's a really important one because standard metrics like intersection over union, IOU, they compare the model's predictions to these potentially flawed labels. So you might get a high IOU score, but it doesn't necessarily mean the model has a true understanding of occupancy. It might just be good at predicting those reflective surfaces that the pseudo-labels captured.
It's like winning a race with a broken stopwatch. You might be fast, but you don't really know your time.
Exactly. And to address this, UniOcc introduces a really clever idea. They call them ground truth-free evaluation metrics. These are ways to measure how well the model is doing without relying on perfect ground truth labels.
That's a really interesting approach. So they're finding ways to measure performance that bypass the limitations of the data itself.
Exactly. It's about finding a more reliable way to judge progress.
Okay.
So we've talked about the quality of labels, but there's another big technical challenge: data fragmentation. A lot of the research out there focuses on single data sets, like nuScenes or Waymo, in isolation.
And each data set has its own quirks, right? Like different sensors or different ways of annotating things.
Yeah, absolutely. They all have different sensor setups, different data formats, different annotation styles. So you can train a model on one data set, but it might not work very well in another.
Like it's learned to drive in one specific virtual city,
Yeah.
but then you take it to a different one and it's totally lost.
Exactly. That's what we call domain shift. And it's a major roadblock for building truly robust autonomous systems. You want a system that can handle anything the real world throws at it, not just one specific data set.
So one of UniOcc's goals is to address this fragmentation problem.
Right. One of their main aims, they want to unify data from multiple sources. They use nuScenes and Waymo, those are real-world data sets, but they also include data from simulations like CARLA and OpenCOOD. This way, the models can learn from a much more diverse set of data.
Okay, so we've covered the problems with labels and the fragmentation of data. What's next on UniOcc's technical hit list?
The next big thing is motion information, or rather the lack of it, and specifically something called per voxel flows in the 3D occupancy labels.
Per voxel flows, that sounds pretty technical. Break it down for us.
Okay, so imagine a 3D occupancy grid. You have all these tiny little voxels, each representing a small volume of space. Now, the current 3D labels mainly tell you if a voxel is occupied or not at a single point in time. They don't really tell you how the stuff inside those voxels is moving.
So we know where things are, but not how they're moving.
Exactly, and that's a problem, right? Because if you want to predict the future, you need to understand how things are moving. Like if a car is turning or a person is walking, just knowing their current position isn't enough. You need to know where they're going.
Right. A car could be stopped at a light or speeding towards you. Big difference.
Huge difference. And that's where per voxel flows come in. These are basically motion vectors. Think of them as tiny little arrows attached to each voxel, showing which direction it's moving and how fast.
So it's like adding a whole new layer of information to the occupancy grid, not just static positions, but actual movement.
Exactly. And UniOcc provides both forward and backward flows. Forward flow tells you where each voxel is predicted to move in the next time step, while backward flow tells you where it came from in the previous time step.
Figure 2 in the paper really helps visualize this. It shows the difference between just assigning a single velocity to a whole object, which doesn't capture rotation or anything like that, versus having individual motion vectors for each voxel, which gives you a much more detailed picture.
Yeah, it's a much richer representation of the scene's dynamics. And figure 3 shows these forward flows in action. You can really see how different parts of the scene are predicted to move.
Okay, and the last technical challenge you mentioned was about cooperation between autonomous vehicles.
Right. There's a growing interest in cooperative driving, where cars can share information to get a better understanding of their surroundings. But there hasn't really been a standard data set for specifically researching cooperative occupancy forecasting.
So if cars could share their occupancy grids and predictions with each other, they could potentially see things they couldn't see on their own, right?
Exactly. Like if one car's view is blocked, another car might be able to fill in the gaps. And UniOcc tackles this head-on. They extend their framework to support multi-agent scenarios using a simulation platform called OpenCOOD. It's the first benchmark that really focuses on cooperative occupancy forecasting.
That's really exciting. It's like giving the cars a way to communicate and work together to build a more complete picture of the world.
It's a big step towards a more collaborative approach to autonomous driving. All right, so we've talked about the challenges that UniOcc is addressing. Now let's get into the framework itself. One of the core elements is the unified data format.
Okay, so this is all about standardizing the data from all those different sources.
Yeah, you've got nuScenes, Waymo, CARLA, OpenCOOD, all these different data sets with different formats and structures. UniOcc brings them all together into one consistent format. So you don't have to deal with all that messiness when you're trying to work with the data.
What are some of the key components of this format?
Well, one of the most fundamental is the semantic occupancy label. It's that 3D voxel grid we talked about, where each occupied voxel is labeled with a specific object category, like car, pedestrian, road, you name it. And Table 2 in the paper shows you exactly how these categories map across the different data sets.
So it's like a universal language for occupancy grids?
Exactly. Everyone's speaking the same language. And it's all centered on the ego vehicle, the car we're focusing on. Forward is positive X, left is positive Y, up is positive Z. It's all standardized. And there's also the option to collapse this 3D grid into 2D for certain tasks.
2D, how does that work?
Well, sometimes you don't need the full 3D information, like for things like planning the car's immediate movements. So you can project the 3D grid onto a 2D plane. And they have a clever way to prioritize what gets shown in that 2D view. Like if there's a car and a pedestrian in the same column, the pedestrian will be shown because, detecting pedestrians is usually more critical for safety.
That makes sense. So it's like creating a simplified view that still highlights the most important information.
Exactly. And then, of course, you've got the camera images themselves, the raw RGB images from all the cameras on the car.
The car's eyes on the world.
Right. And then there's a camera field of view mask, which tells you which parts of the 3D grid are actually visible to each camera.
So you know what each camera can and can't see.
Right. That's really important for handling occlusions, when things are blocking each other's view. And to link those 2D images to the 3D world, you've got camera intrinsics and extrinsics. These are parameters that describe the camera's internal properties and its position and orientation relative to the car.
It's like the calibration information for the cameras.
Yeah, exactly. Then you've got the ego-to-world transformation, which tells you where the car is in the overall world.
It's like the car's GPS coordinates, but more precise.
Right. It's a transformation matrix that lets you place the car and all the sensor data into a global coordinate system. And of course, there's the forward and backward occupancy flow we talked about, these per voxel motion vectors, giving you that detailed motion information.
And to round it all out, there are object annotations, right?
Yes. These give you information about individual objects in the scene, their position relative to the car, their size, their category, everything.
So with this unified data format, researchers can really dive into a wide range of tasks, right?
Absolutely. You can do occupancy prediction, where you're trying to estimate the current 3D occupancy grid from past camera data. You can do occupancy forecasting, where you're predicting how that grid will change in the future.
You can even do cooperative occupancy prediction and forecasting, where multiple cars work together.
Exactly. And the great thing is, UniOcc doesn't just provide this unified format. It also brings together data from all those different sources we mentioned. nuScenes, Waymo, CARLA, OpenCOOD. It's a one-stop shop for occupancy data.
And each of these data sets has its own strengths, right?
Yeah, definitely. nuScenes and Waymo are real-world data sets, so they give you that complexity and messiness of the real world.
Yeah.
But they don't have native 3D occupancy labels, so UniOcc generates those using multiple methods to make them as robust as possible.
It's like they're reconstructing the 3D world from the 2D images and LiDAR data.
Exactly.
Yeah.
Then there's CARLA, which is a simulator. So you get perfect ground truth labels because you have access to the underlying 3D models of the environment. And you can create all sorts of different scenarios, which is great for training.
And OpenCOOD is built on top of CARLA, but it focuses on multi-vehicle scenarios.
Right. So it's perfect for studying cooperative driving. You get the simulated environment with multiple cars interacting, and you can extract the 3D occupancy information from those simulated scenes.
It's like a virtual playground for cooperative driving research.
Exactly. But UniOcc goes beyond just providing data. It also comes with this really handy unified occupancy processing toolkit. It's a set of tools for analyzing and working with the occupancy grids.
What kind of tools are we talking about?
Well, one key feature is object identification. You can take a raw occupancy grid and identify the individual objects within it. It involves a few steps. First, you extract all the voxels that belong to a specific category, like all the car voxels. Then you use connected component labeling to group those voxels into separate object instances. Then you gather the coordinates of all the voxels for each object. And finally, assuming the objects are on a flat ground plane, you fit a horizontal bounding box around each object and extract its dimensions: length, width, height. Figure 5 in the paper shows the whole pipeline visually.
So it's not just about blobs of occupancy, it's about recognizing actual objects in the scene.
Exactly. And then there's object tracking. You can follow an object across multiple time steps, see how it moves. They use the per voxel flow information for this. For each object, they predict where its voxels will be in the next frame, calculate the center point of those predictive voxels, do the same for the actual observed object in the next frame, and then use the Hungarian algorithm to match them up. So you can keep track of individual objects as they move through the scene.
Very cool. You can see where that object's going.
Yes. And then there's object alignment, which lets you analyze the shape of an object. It involves translating the object's voxels so that its center point is at the origin of the coordinate system, and then using principal component analysis, PCA, to find a consistent orientation for the object. So no matter how it's actually oriented in the scene, you can align it in a standardized way to compare its shape across different frames.
So it's like taking a 3D scan of the object from a standard viewpoint, even if it's moving and rotating in the scene.
Exactly. It's great for studying shape consistency over time.
Yeah.
Okay, so we've got all this data, all these tools. Now, how do we actually evaluate How well these models are doing. UniOcc provides a comprehensive set of unified evaluation metrics.
And they're going beyond just the standard metrics, right, because of those limitations with ground truth labels that we talked about.
Exactly. They build on the standard voxel-based metrics like geometric intersection over union, IOU, and mean IOU, MIOU. These metrics look at the overlap between the predicted occupancy grid and the ground truth grid.
But they also introduced those new ground truth free metrics.
Yes, that's one of the big innovations of UniOcc. Because sometimes a high IOU score doesn't tell the whole story. It might just mean the model is good at predicting those flawed labels. So they came up with these new metrics that don't rely on perfect ground truth.
Tell us about these ground truth free metrics. What are they looking at?
The first one is key object dimension probability. It looks at the dimensions of a predicted object, its length, width, and height, and it compares them to a Gaussian mixture model, GMM, that's been trained on real or synthetic data for that object category. So it can tell you if the predicted dimensions are realistic for that type of object.
So it's like checking if the car is the right size for a car.
Exactly. Then there's temporal foreground object shape consistency. This metric looks at how stable the shape of a predicted object is over time. They align the object's voxels across different frames and calculate the IOU of those aligned shapes. A high score means the model is predicting a consistent shape, even without perfect ground truth.
Like the car shouldn't be morphing or changing shape drastically from frame to frame.
Exactly. And then there's temporal background environment consistency. This one focuses on the static parts of the scene, like roads and buildings. It checks if the predicted occupancy of those areas remains consistent over time. Basically, it projects the background voxels from one frame to the next based on the car's motion and calculates the IOU of the overlap with the observed voxels. So it can tell you if the model is maintaining a stable representation of the background even without perfect labels.
Very clever. So these ground truth-free metrics are all about looking for consistency and plausibility in the predictions.
Exactly. They're moving away from just chasing scores on potentially flawed benchmarks and towards evaluating a more fundamental understanding of the world. Okay, so now let's talk about what they actually found when they used UniOcc to evaluate different models.
What were some of the key takeaways from the experiments?
Well, they learned a lot. One of the big things was the impact of flow information. They took an existing model called Ockworld and added in the flow information from UniOcc. And guess what? It significantly improved performance.
So having that detailed motion information really makes a difference.
Big time. Table 3 in the paper shows the results. They saw consistent improvements in both IOU and MIU on both nuScenes and Waymo. And the gains were even bigger for the category averaged MIU, which suggests that the flow information is especially helpful for predicting the movement of dynamic objects like cars and pedestrians.
So the model can better understand where things are going because it knows how they're moving.
Exactly. They also trained a separate part of the network to directly predict the flow for the next time step, using the ground truth flow from UniOcc as supervision. Now, another big area of investigation was cross-domain performance. How well models trained on one data set generalized to others.
And how did they fare in those experiments?
It was really interesting. Table 4 has all the details. One of the key findings was that using diverse data is beneficial, even for in-distribution performance. So even if you're testing on the same data set you trained on, training on a mix of data sets can lead to better results.
It's like the model becomes a more well-rounded driver by experiencing different environments.
Exactly. And they also found that diverse data is crucial for out-of-distribution generalization. Models trained on a single dataset really struggled when tested on new datasets. But the model trained on the unified UniOcc dataset, with data from nuScenes, Waymo, and CARLA, consistently performed better across all the test sets, even those it hadn't seen before.
So if you want a model that can handle the real world, you need to train it on a wide variety of data.
Absolutely. And they also looked specifically at the role of simulation data. And they found that it's really helpful for learning object shapes, because in CARLA, you have perfect shape information from the 3D models. And when they included that data, the models were better at predicting accurate object shapes, especially for cars.
It's like the simulation data helps fill in the gaps and provides more complete information than you can get from real-world data alone.
Yeah, exactly.
Yeah.
The figure 6 shows this really well. You can see the difference in car shape prediction when CARLA data is included. And they also found that diverse data helps maintain accuracy over longer prediction horizons. So the further you predict into the future, the more challenging it gets. But the models trained on multiple data sets were better at maintaining accuracy over those longer time frames.
So it's not just about being accurate in the short term, it's about making reliable predictions further into the future.
Exactly. And finally, they found that combining real and synthetic data also improves background environment forecasting. So it's not just about the dynamic objects like cars and people. It's about understanding the whole scene, including the static elements.
So overall, it seems like this unified, diverse data set is really paying off. The models are more robust, more accurate, more generalizable.
Definitely. And they also included a quick evaluation of some existing occupancy prediction models. Table 5 shows that CVTOSH generally outperformed CAM4Doc, probably because of its more advanced way of fusing information over time, and they also showed some preliminary results for cooperative occupancy prediction, which looks really promising. Table 6 shows that sharing information between cars can lead to better performance.
So there's a lot of potential for cooperative perception to really enhance safety and performance.
Absolutely. Okay, so let's step back and think about what all of this means. UNOcc is a big step forward for research in autonomous vehicle perception. It addresses some key limitations in the field and provides a more unified and comprehensive framework for moving forward.
The technical innovations, especially the per voxel flows and the ground truth-free metrics, are really changing the game. And the findings highlight the importance of diverse data for building truly robust systems.
Definitely. And those early results in cooperative perception are really exciting. It's a glimpse into a future where cars can work together to understand the world around them.
Well, I think that's a great place to wrap things up. This deep dive into UniOcc has given you a solid technical understanding of this important development. For those who want to learn even more, check out the Neural Intel webpage. We'll have the paper linked there, along with other cutting-edge research. And let us know what you think. What stands out to you about UniOcc? What further technical explorations do you think are needed?
We encourage everyone to dive deeper into the UniOcc paper and explore this fascinating field. There's so much more to discover, and the future of autonomous driving is being shaped right now.
Thanks for joining us today, and we'll see you next time on Neural Intel.
See you next time.
Bye.